Good morning, everyone. My name is Shuja Bashir Malik. I am a PhD student at NO₂ Research Group, Universitat Rovira, Virgili, Tarragona, Spain. Today, I'm going to discuss about room temperature detection of ppb level nitrogen dioxide by tungsten disulfide sensors. So I'll start my presentation with the outline that I'll be discussing later in the presentation. So the first slide would be why do we need to detect nitrogen dioxide? And then I will move towards next generation materials for gas sensing, followed by tungsten disulfide synthesis and characterization. And then I will move towards the gas sensing procedures that we follow in our lab, followed by gas sensing results and sensing mechanism. Then at the end of the presentation, I will discuss some conclusions and future perspectives. So the big question, why do we need to detect nitrogen dioxide? Nitrogen dioxide is a toxic gas with its sources being burning of fossil fuels, which includes vehicular emission, factories, industries. The natural sources of nitrogen dioxide are volcanoes. Since nitrogen dioxide is a toxic gas, it has some adverse effects, one being acid rain and smoke. I myself, being an Indian, I know these things very well, and you can see Taj Mahal here. So it has been completely kind of devastated because of the acid rain, and now has been restored back to its former glory. Talking of adverse effects of nitrogen dioxide, one of the main adverse effects of nitrogen dioxide is respiratory problems. According to European Environment Agency, there have been 166,000 premature deaths due to NOx species in European Union alone in 2022, which demands for a precise detection of nitrogen dioxide. So moving on to the next generation material for gas sensing, we say that the next generation materials for gas sensing are transition metal dichalcogenides, or shortly we call them TMDs. So the characteristics of TMDs is that they have a tunable band gap. For example, in case of tungsten disulfide, in bulk form, the tungsten disulfide has an indirect band gap. And when we synthesize the monolayers of tungsten disulfide, the band gap changes to direct band gap. And they are characterized by large specific surface area. And since they are TMDs are layered materials, they have large specific surface area. And unlike metal oxides, they work at room temperature mostly. And we have an option to grow TMDs with edge-enriched growth. Also, TMDs are characterized by desired semiconductor properties. As I mentioned here, that they have the tunable band gap, we can grow N-type material or P-type material. Also, as I mentioned here, that they are layered materials, so we have an option to grow TMDs in nanoscale thickness. So how do we do tungsten disulfide synthesis in our lab? We use an atmospheric pressure chemical vapor deposition furnace, which has different temperature zones. So we purge the furnace with argon before starting the reaction so as to get rid of any trace oxygen. And then we use tungsten trioxide powder as a precursor for tungsten disulfide. And we use 2 sulfur boats with equal amount of sulfur. And the reaction is carried out at 900 degrees centigrade. And the yield of our reaction is in hundreds of milligrams in powder form, so which gives us the flexibility to deposit the material onto virtually any kind of substrate. The synthesis method is facile and is a one-step method, and also it has a potential for industrial scale. Moving on towards the sensor fabrication, we use our homemade airbrushing system to fabricate our sensors on alumina substrates typically. So what we do is we generally make a solution of the TMDS and in a solvent of our choice, and we use a commercial airbrush to deposit the films on the substrates. The substrates we keep on hot plate in order to make sure that we get reproducible films with reproducible thickness and resistance. We connect the substrate real time to a multimeter to monitor the resistance real time so as to get reproducible thickness films. We use nitrogen as a carrier gas to transport the material to the substrate. And in order, this gives us also an option or flexibility to deposit the films on any kind of substrates. Moving on towards the characterization of the deposited material, we do field emission scanning electron microscopy. As you can see here, we have a layered, or we have plate-shaped tungsten disulfide, which is a 2D growth of the material with an average thickness of 30 nanometers. And to confirm that this really is tungsten disulfide, we did high resolution transmission electron microscopy. You can see here the material is layered, which also we checked, we dived deep into the characterization. The interlayer distancing is 0.22 nanometers, confirming that the material is really tungsten disulfide and is in agreement with X-ray diffraction. Also, the layers are highly crystalline. Moving ahead towards XRD, X-ray diffraction, it confirms the full conversion of tungsten trioxide to tungsten disulfide and confirms the material is highly crystalline. Moving ahead towards Raman spectroscopy, the results confirm that our material is a layered material, a multi-layered material actually. So moving ahead towards the gas sensing procedure, this is a homemade gas sensing system that we have in our lab. So we use calibrated cylinders of gas and synthetic air, which are followed by a network of mass flow controllers and valves, which deliver exact and precise amount of gas to the Teflon test chamber. The chamber has the capability to hold 4 sensors simultaneously. In here, we have an option to add a power supply to heat the sensors to desired temperatures. Then we use Agilent data acquisition system to record the resistance changes of the sensors when exposed to analyte gases. And here is an example. Okay, moving ahead towards the gas sensing results. So this is the resistance dynamics of our tungsten disulfide sensor towards 100 parts per billion of nitrogen dioxide. As you can see, the responses are stable and reproducible, and there is a minimum baseline drift. And moving ahead towards the response with increase in temperature, we have the best responses at room temperature, approximately 28%. And as we increase the temperature towards 100 degrees, the responses decrease sharply, with no responses approximately at 100 degrees. We, for your information, we used the formula, this one, for calculating the response percentage. In order to check the selectivity of our sensors towards different analyte gases, we use both oxidizing and reducing gases. So our sensors are highly selective towards nitrogen dioxide at room temperature with 28% of response, and all the other gases have minimum responses. For example, in case of 10 ppm of benzene, there is only 7.3% of response. So we can say that our sensors are highly selective to nitrogen dioxide with low cross sensitivity. So I will discuss a little bit about the gas sensing mechanism. So our sensors, we propose that the sensing mechanism of our sensors is based on the physisorption at the edges, since we have 2D material with edges and a large number of edges, and our reaction is a sulfurization reaction, which makes it possible to have additional sulfur edges on the material. And our material behaves as a p-type material. The vertical growth of our material enhances the sensitivity and selectivity towards NO₂, and the decrease in the resistance is due to the injection of the charge towards the gas molecules. So for conclusions and future perspectives, for conclusions, we have developed a facile method for large-scale production of tungsten disulfide. The synthesis method is highly reproducible with industrial scale potential, since we have hundreds of milligrams of yield of our material. And we have the material we get is in powder form. That's, as I mentioned, gives us the flexibility to deposit on any kind of substrate. So since we checked the gas sensing response towards 100 ppm of NO₂, and it's promising and stable at room temperature, and the sensors are highly selective towards nitrogen dioxide with low cross sensitivity towards other gases. So we have an in-house built airbrushing tool, which gives us the option to deposit thin films of reproducible thickness. In case of future perspectives, we are planning to do the gas sensing measurements in humid environment, and then maybe we will, in future, decorate the material with metals and metal oxide nanoparticles. Thank you very much for your attention, and we are open for collaborations.